Is the screen visible?
Yes, ma'am.
Okay. So let us start. In the last class, we were discussing the PN junction, and today we are going to continue that discussion and get introduced to a few more concepts. So while discussing the PN junction on this slide, what we said that here you have two different type of semiconductors put together to form a junction. So there's a p-type semiconductor and there's an n-type semiconductor. So while these p-type and n-type semiconductors could be individually graded, but if you look at the junction over here, this is definitely graded because if you see over here in the P type of semiconductor, the holes are the majority carriers. So this side of the junction, holes are in majority, while this side of the junction, holes are in minority. Similarly, if we talk about N type, so this side of the junction, electrons are in majority, and this side of the junction, electrons are in minority. So that means definitely at the junction, there exists a gradient of majority charge carriers, which causes the movement of electrons from this side to this side and for holes from this side to this side. So this process is known as recombination, where the electrons, they move towards this side and holes, they move towards this side, and then they recombine and disappear. This recombination is caused by the diffusion of majority carriers across the junction. This is what we saw in the last class. So one thing that I did not mention in the last class is that this diffusion of electrons from N type to P type and from P type to N type, तो ये जब recombination हो रहा है, this time, this leads to a flow of small current, which is actually called as the diffusion current. That is, at the junction, because of concentration gradient, you will have the movement of holes towards the N type and movement of electrons towards this side, P type, and this net effect results in the flow of diffusion current. And what will be the direction of diffusion current? What will be the direction of diffusion current? So let's say this is the right side and this is the left side. So we know that holes are moving from here to here. That means holes are moving from left towards the right, and electrons are moving from right towards the left. And the direction of flow of current, if we look from the holes perspective, this is towards the right. And if we look from the perspective of electrons, because electrons are moving to the left, that means here also the current movement will be considered towards the right. So due to the process of diffusion, the diffusion current starts flowing across this PN junction, and the direction of diffusion current is towards the right side of this PN junction. So this is the first type of current that you will find in the PN junction. Now, next thing what we said that because of the process of recombination happening in this depletion region, holes will recombine with electrons, and in the vicinity of this depletion region, there will be no free mobile charge carriers. There will only be positively and negatively charged ions, because all the majority carriers have crossed the junction and eventually recombined. So this region becomes depleted of majority charge carriers. That's why we call this as the depletion region. So what happens now in the depletion region, since there are no mobile charge carriers and there are only ions, so this establishes an electric field. This establishes an electric field at the junction. And what does this electric field do? This electric field exerts the force on the majority charge carriers. So in the last class, we studied that the presence of electric field forces the majority charge carriers to flow from the region of low concentration to the region of high concentration. This I mentioned to you in the last class. तो यहाँ पे क्या हुआ? Because of the presence of these positively and negatively charged ions, some electric field E is created. Now, we also know that these N-type and P-type semiconductor part is itself graded, and this is actually graded such that the concentration of the grading increases as we move away from the junction. So at the junction, the concentration is minimum for the holes, and as you move away from the junction, the concentration increases. Likewise, over here, the concentration for electrons is minimum at the junction, and then as you move away from the junction, the concentration increases. So now what happens? Because of this electric field, जो कि ions की वजह से यहाँ पे create हो गई है, the electrons in this N-type are pushed towards the right. So these electrons will be pushed towards the right, whereas the holes, these will be pushed towards the left. Or instead of push, we will say drift, because this is the word that actually will define another type of current. So because of the electric field of these uncovered ions which are present in the depletion region, a force is exerted on the electrons and the holes, which causes them to drift towards the right for the electrons and drift towards the left for the holes. So this drift causes another type of current which we call as the drift current. So in the PN junction, then there are two types of currents. First current is the diffusion current and second current is the drift current. What is the difference between them? The difference between them is diffusion current occurs naturally because of the difference in the concentration of majority carriers on either side of the junction, whereas for drift current, you need an electric field, which is in turn created due to the process of diffusion. And in the absence of any external voltage applied, the sum of diffusion current and drift current will always be equal to 0. If there is no external voltage applied, then no net current flows through the PN junction. So we say that the diffusion current and drift current should be equal and opposite in that case. Is it fine?
Ma'am, what is the cause of the drift current?
Drift current is caused because of this electric field. So we said that junction mein, in the vicinity of the junction, the holes and electrons will recombine with each other. So is region mein, there will not be free electrons or holes. Only positively and negatively charged ions will be present. So these positive and negative charged ions in the vicinity of the depletion region establish an electric field, which in turn forces other holes and electrons to drift, causing the drift current.
Okay, got it.
Okay, so now this concept will be useful to understand how the diode is going to function. So let's see now how do we create a diode out of this PN junction. So creating a diode out of the PN junction is very easy. You have a PN junction already. And then what we do is we place metallic contacts, or we pull out a metallic contacts from either end of the PN junction. So this creates a circuit element that we call the diode. So you can understand that this is simply a PN junction with one metallic end towards P side and one metallic end towards the N side. The symbol is as shown over here. So this will be a triangle placed along with a vertical line. So this triangle, this denotes the P side, and this vertical line, this denotes the N side. So this P side is also called the anode and the N side is also called the cathode. Now Now, when you connect this into a circuit, it is very important to observe how this is connected. So there could be two possibilities how this is connected across any external voltage source. So first of all, we define the term biasing. What is biasing? Biasing is the application of external DC voltage to a diode. Keep in mind that here we are talking about the DC voltage and not AC voltage. So whenever you apply any positive or negative voltage across this diode, we say that we have biased a diode. And then there could be two possibilities to bias a diode. The first possibility is forward bias and the second possibility is reverse bias. Forward bias में क्या होता है? The P side of the diode is connected to the positive of the battery. So for example, if this is my diode and I connect this such that this P side or the positive side is connected to the positive of the battery and the negative side of the diode is connected to the negative of the battery. So this is the condition of forward bias. And how about the reverse bias? In case of reverse bias, the positive of the diode is connected to the negative of the battery. And the negative of the diode is connected to the positive of the battery in this manner. This arrangement or this setup is known as reverse bias. And why it is important to observe if the diode is in a forward bias state or if it's in a reverse bias state, because depending upon forward bias or reverse bias, the way of functioning the diode will change. So let us start with reverse bias. So here in figure shown figure 6.11, they have shown the reverse biasing. So here you see this is the positive side, P side of the diode, and this is the N side of the diode. And as we just mentioned, here P side is connected to the negative of the battery and the N side of the diode is connected to the positive of the battery. So now what happens? So let us visualize this diode in the form of a PN junction as shown over here in this adjacent figure, and this is again shown in a reverse bias connection in the battery. So now what happens? अभी last slide में हमने क्या पढ़ा था कि the holes, they have the tendency to diffuse to the right and drift to the left. So these are holes, just for the clarity. This is my right and this is my left. So holes क्या करते हैं? They will diffuse towards this side and they will drift towards this side. Similarly, my electrons, they have the tendency to diffuse to the left side and drift towards the right side. Now, when this PN junction is connected across the battery in this fashion, what happens is that all these are holes, and we know that holes have positive charge. And here this is the negative of the battery. So this is the negative charge. So what happens is that this negative of the battery kind of attracts this positive charge. Similarly, over here, the positive of the battery, this kind of attracts this negative charge on the electron. So this attraction, what does it do? It pulls away kind of all the majority carriers towards the extreme end of the diode. That means depletion region starts widening. So earlier we know that the voltage across the depletion region was V0. That was my barrier potential. That was my barrier potential. But when I connect the PN junction in a reverse bias connection, the depletion region widens and it keeps on widening until the barrier potential becomes V0 plus capital V. Okay? So the first thing is when I apply reverse bias, I am actually widening the depletion region. Why? Because the holes will be attracted to the negative side of the battery and the electrons will be attracted to the positive side of the battery. So this is the first thing. The second thing is that now we know in the N type, holes are the majority carriers. So here we do have a lot of electrons, but also there are a few holes which are minority carriers in the region. And these holes, as we know, they will have the tendency, they already have the tendency to drift to the left. At the same time, left, say there is some force of attraction also. So what will happen? These minority carriers from the N region, they will be drifted into the depletion region towards the left. And when these holes enter the depletion region, the electric field present in the depletion region further push these holes into the P region. Similarly, over here in the P region, we know that electrons are the minority carriers and electrons have the tendency to drift to the right. This is their natural tendency, but we have also applied the positive charge over here towards the N side. So these electrons will be drifted into the depletion region. And in the depletion region, due to the presence of electric field E, these electrons will be further pushed into the N region. So this movement of minority carriers across the junction, movement of minority carriers across the junction causes a flow of small current, and this current is known as the reverse saturation current of the diode. This current is known as the reverse saturation current of the diode. And what will be the direction of this reverse saturation current? So we have holes over here and holes are moving towards the left. So the whole current is towards the left. We have electrons over here and electrons are moving towards the right. So due to the flow of electrons, also the flow of current will be towards the left. So the net reverse saturation current which flows through this PN junction is towards the left. This is how it is shown over here in this circuit diagram. So what is the takeaway? The takeaway is that whenever you have a PN junction in a reverse bias state, then a very small current flows through the PN junction diode due to minority carriers, and this current is known as the reverse saturation current. And one thing that you need to keep in mind is that this reverse saturation current does not depend upon V. So let me call this reverse saturation current as IS. So IS does not depend upon the value of V, rather IS is a function of temperature. So if I increase the temperature, then more electron hole pairs will be generated. That means we have more minority carriers and therefore the reverse saturation current will be more. Then what will happen if I further increase this value of voltage? So I know that in the reverse bias condition, very small reverse saturation current will flow through the PN junction diode. But then if I keep on increasing the value of V, so if the value of V is increased to a sufficiently large value, then what happens? Then the junction breaks down. What do I mean by junction breakdown? So if this voltage is large, the electric field E, which is created across the junction, becomes very strong and it starts breaking pretty much all the covalent bonds present in the P and the N side, which leads to the formation of lot of majority carriers, causing a very large current to flow through that. So in the nutshell, what is happening? When the PN junction diode is reverse biased for a given value of V, there will be a very small flow of current due to minority carriers. We call this current as the reverse saturation current, which is not dependent upon V, but it's a function of temperature. Then if I keep on increasing the value of V to a sufficiently large value, then in that case, the junction will break down. Means the electric field will become strong enough to break pretty much all the covalent bonds, thereby creating lot of majority carriers that will contribute to the flow of very large current. Is this understood?
Ma'am, in the initial case when there is less current,
Hmm.
so is that current only due to the reverse saturation? Because there are other currents also. So is does not add up.
No, that does not add up. That does not add up because यहाँ पे क्या हो रहा है, जो मेजॉरिटी कैरियर्स थे दे आर बीइंग पुल्ड अवे फ्रॉम द जंक्शन. They are pulled away from the junction, so पूरे circuit में there cannot be any current because of the flow of majority carriers. Only when this junction is crossed, then you can say that the current is flowing through the PN junction. So reverse bias के केस में जो majority carriers होते हैं वो junction को cross नहीं कर पाते because opposite direction में उन पे force लग रहा होता है. So you have current only due to the presence of minority carriers.
Okay.
Okay. So your junction break, yeah.
Ma'am, so the large current is drift current?
Yes, in fact, reverse bias के केस में जो भी current flow होता है, this is due to the drift current, due to the drift or the electric field. So this is kind of a drift current.
Okay.
Reverse saturation current is also drift current. और बाद में जब breakdown हो जाएगा और reverse saturation current की value बहुत ज्यादा हो जाएगी, तो वो भी drift current ही होगा. ठीक है? Okay. So now one more thing I would like to mention over here is that when the junction breaks down, so when the junction breaks down, what happens? It's not that the very large value of current which is flowing through the diode will now damage the diode. I mean, it could damage the diode also. It depends. There are two types of breakdowns actually, the Zener breakdown and the avalanche breakdown. So we will not go into the details because this is not required right now. But the idea is not all the breakdowns will cause the diode to damage. In fact, if you talk about the Zener breakdown, then what happens is that this breakdown causes very large current to flow through the diode, which in turn helps to maintain constant current across the load. So do not worry about this fact, Abhi, because while we study the Zener diode, maybe in next class or next to next class, we will study about this in very detail. The point over here is that breakdown is not always a bad thing because it helps to devise special applications of the diode like voltage regulator. So when we study voltage regulator, you will see that in this case, the diodes are always operated in the breakdown region because it will help to maintain constant voltage across the load. But in general case, because here we are not talking about the breakdown at all, we just mentioned it as a special phenomena. So in general, we do not want our diode to go into the breakdown region. Therefore, it is essential that we choose this value of voltage carefully. So this was all about the reverse bias. Now let us see what happens in the case of forward bias. So again, we will have a PN junction as a यहाँ पे there are exposed ions, and then there are majority carriers, holes over here and electrons over here, and this is forward biased. Forward biased means the P side or the positive side will be connected to the positive of the battery and the N side will be connected to the negative of the battery. So अब क्या होगा if we go by the previous logic, this side is positive and the holes also carry a positive charge. So this is going to cause a repulsive effect on the majority carriers. Similarly, in case of electrons, so they carry negative charge and this is connected to the negative of the battery. So here there will be a repulsive effect which is going to push the majority charge carriers towards the junction. And when the value of V is large enough, the tendency of diffusion will overpower the tendency of drift and the majority carriers will start flowing across the junction, thereby leading to the flow of what we call as forward current. Okay? Also, you can understand that over here when there's a repulsive force, the electrons are pushed towards the junction, the holes are also pushed towards the junction. So जो depletion region का width था पहले, that width reduces. So when the width reduces, it becomes easy for the majority charge carriers to cross over the junction. So this is one of the possibility. And then the other thing is they naturally cross this because there is some external force which is coming because of the application of this voltage. But this voltage has to be sufficiently large. How much large? It should be greater than the cut-in voltage of the diode. So until you have a cut-in voltage, the value of forward current will be very small, maybe because of the diffusion that was happening naturally on its own. But if the value of V increases beyond the cut-in voltage, then what happens? The tendency of drift is overcome by the tendency of diffusion, and pretty much all the majority charge carriers start crossing the junction, thereby leading to the flow of forward current across the PN junction. Okay? So from here we will see that this forward current is actually a
Ma'am, so
diffusion current.
ma'am, so what happens in the depletion region? Is it like devoid of any charge inside the depletion region?
Yeah, so depletion region तो बना ही इसलिए था because, so I'll just create this depletion region. So we saw that depletion region was earlier created because there were no free charge carriers in this region, right? This was when I applied, when I did not apply any voltage. Now, when I applied the voltage, so what happens? All the majority charge carriers that were present over here, electrons in the N side and holes in the P side, they are pushed towards this side because of the repulsive force. Okay? So in that case, what will happen? इसका width जो है वो कम हो जाएगा. I mean, पहले हो सकता है दो rows ऐसे हों जहां पे कोई फ्री मेजॉरिटी कोई फ्री मोबाइल चार्ज कैरियर्स नहीं थे, बट बिकॉज ऑफ दिस रिपल्सिव फोर्स these holes and these electrons from here start filling in the depletion region. So first of all, this depletion region is going to reduce its width, but it will not completely disappear. ऐसा नहीं है कि repulsive force की वजह से पूरा depletion region चला जाएगा, because there is some inherent bulk resistance of the semiconductor itself which will cause certain minimum width to be always present in the depletion region. So say जितना भी फिल कर सकते थे डिप्लीशन रीजन को, उतना ये मेजॉरिटी चार्ज कैरियर्स ने फिल कर दिया. नाउ इन दिस स्टेट यू हैव बीन लेफ्ट विथ मिनिमम विड्थ ऑफ द डिप्लीशन रीजन, एंड ड्यू टू द एक्सटर्नल फोर्स ऑफ द वोल्टेज, जो रिपल्सिव फोर्स यहां से लग रहा है, इट्स पॉसिबल फॉर दीज मेजॉरिटी चार्ज कैरियर्स टू जंप अक्रॉस दिस मिनिमम विड्थ ऑफ द डिप्लीशन रीजन. ठीक है?
Yes, ma'am.
Okay. So what will be the direction of this forward current? Can anyone tell me? So these are the holes. Let us say that this is right and this is left. So these are holes. They are being pushed towards the right, and the electrons, these are pushed towards the left. So what will be the direction of diffusion current in this case?
Left to right.
From P junction to N junction.
Yeah, left to right, or from P to N. So drift current की direction was towards the left, but the direction of forward current would be towards the right. Okay. So now, again, to sum everything up, in the reverse bias region, we had only small current, which was due to the presence of minority carriers. We called that as the reverse saturation current, whereas in the forward region, you will have some actual current flowing through the diode, and this is known as the forward current. The difference is that reverse saturation current was drift current, whereas the forward current is a diffusion current. So now when we are comfortable with this, let us try to define what is the relationship between the voltage and the current in case of a diode. From the starting of this course, we have been saying that the diode is a non-linear device. It's a non-linear device because V directly proportional to I is not valid in this case. So then what is the formula? The formula is or let me write it here in the previous page. If we want to see the relation between V and I, so if this is my diode and this is the small, no, this is not the small current, but this is the forward current. This is the forward current which is going to flow through this diode, causing a voltage drop of small v, then the relation between V and I is given as I is equal to I reverse saturation multiplied by e raised to the power of V divided by eta Vt minus 1. So this is the relation that holds good for relating the voltage drop across the diode and the current flowing through it. So from here you see that I is not directly proportional to V, or V is not directly proportional to I, because V occurs in the exponential while finding out the value of this current. So here what are these terms? Vt. Vt we already know, this is the volt equivalent of temperature. And this is given by T divided by 11,586, where T is the temperature in Kelvin. And what about eta? Eta is called the emission coefficient. Eta is called the emission coefficient and its value is 1 for germanium and eta is equal to 2 for silicon. And if you rearrange this mathematical formula a little bit, then you can also have the expression in terms of voltage. So the voltage drop across the diode, given that current I flows through it, this will be given by eta into Vt ln of I divided by Is plus 1. And one thing we need to keep in mind that these expressions for I and for V are valid only in the forward bias region. In the reverse bias region, we do have a small current, that is my reverse saturation current, but this is actually the property of the material itself. You cannot find that by using any formula. Of course, you can find that by this formula given some forward current, but otherwise Is is actually the property of that particular material. So for example, for germanium, this is on the order of microamperes, while for silicon, this is on the order of nanoamperes. So whenever the semiconductor materials are purchased, generally the value of reverse saturation current is mentioned on the specification sheets. So here this small I is actually I forward current. Okay, so from here we validate that the relation between I and V in case of the diode is non-linear. Now let us have a look at the IV characteristic of the diode. Yeah.
What does that volt equivalent of temperature actually mean?
And this is a constant, right? So in the last class we saw that the diffusion constant and mobility are related by Einstein's equation. If you remember, dN by mu n was equal to dP by mu p, and this was equal to a constant value Vt, which is given by kT by Q, where T is the temperature in Kelvin, K is Boltzmann constant, and Q is the charge on, 1 unit charge. So Vt can be assumed to be a constant.
Okay.
Okay, so next we are going to see the IV characteristics of the diode. So IV characteristic is simply a plot that relates the voltage drop across the diode with respect to the forward current. So here at the center, the value of voltage is 0. Here the value of voltage is positive, and here the value of V is negative. So this region, this first quadrant, is the quadrant where the diode is forward biased, and this third quadrant is the region where the diode is reverse biased. So the characteristics shows in the plot what we have just now learnt in words. So क्या होगा forward bias region में? So initially until some small value, so this is not actually reflected over here. Generally, this is of the type like this. Initially, it is very small and then it increases in this manner. So initially, for very small value of voltage, say until the cut-in voltage V gamma, the value of current is very small, and then after V gamma, you will have a rapid increase in the value of current, which will be governed by this equation. Similarly, what will happen in case of reverse biasing? So as the voltage becomes negative and the diode is reverse biased, we will have reverse saturation current flowing through the diode, which is a very small value, and it's going to remain constant as long as I am below the breakdown voltage. So this breakdown voltage is also sometimes called the Zener voltage. That's why it is denoted by VZ over here. तो जब तक VZ नहीं आएगा तब तक very small reverse saturation current will flow through the diode, but once the voltage exceeds the Zener voltage, then the junction breaks down and the value of reverse saturation current increases in a very steep manner. And here you see for all this, in all this region, when the current is increasing, now voltage does not increase. So that means while you are working in this region, the voltage actually remains constant. So these are the IV characteristics of the diode. In the forward region, it will be defined by this curve, which shows the forward current, whereas in the reverse region, it will be shown by this almost constant curve in the region between 0 to VZ, and then by steep increase for the voltages beyond VZ.
V gamma is the potential required to overcome the barrier potential, right?
Yes, overcome the barrier potential, wherein the tendency of diffusion becomes greater than the tendency of drift. That is my V gamma or cut-in voltage. So this is true in general for any diode. Now let us compare the diode behaviors. So first diode here, this is a germanium diode and this is a silicon diode. So reverse saturation may, so almost the behavior is same, just that the reverse saturation current for germanium is more than silicon, but let us see what's happening in the forward bias region. So first thing that we observe over here is the cut-in voltage. For germanium, the cut-in voltage is 2. For silicon, the cut-in voltage is somewhere around 0.5. So iska cut-in voltage is less than the cut-in voltage of silicon. What does that mean? That means for a given value of voltage, germanium diode will have large current compared to the silicon diode. What do I mean by that? So for example, I want to see what is the current flowing through the germanium diode at 0.25. So this will be somewhere over here. This is something like, say for example, it's 25 milliamperes. So at 0.25 volts, the value of current in the germanium diode is 25 milliamperes. But if you see over here for 0.25, what is the current that is flowing in the silicon diode? It's almost negligible. This is almost negligible. That means for a given value of voltage anywhere on the x-axis, the current flowing through the germanium diode is more than the current that flows through the silicon diode. So is it a good thing or a bad thing? So one can say that ठीक है, for a given voltage मुझे germanium diode में ज़्यादा current मिल रहा है, so let me prefer germanium over silicon. But this is not true. Why this is not true? Because of the reverse saturation current. So we have already seen that for germanium, reverse saturation current is on the order of microamperes, whereas for the silicon diode, the reverse saturation current is on the order of nanoamperes. So lower reverse saturation current is what we want, because if the reverse saturation current is high, first of all, it will lead to heating effects in the diode, and secondly, the recombination of the minority carriers actually hinder the flow of the majority carriers. So that's why having high value of IS is not preferred. Therefore, most of the devices, semiconductor devices, they are made up of silicon. Okay? Okay. So now let us see how does these diode currents, they vary with the temperature. So earlier we have seen that reverse saturation current is a function of temperature. How does it vary with temperature is what we are going to see now. So it has been experimentally determined. It has been experimentally determined that for silicon as well as for germanium, the reverse saturation current is going to double itself for every 10-degree increase in temperature. So for every 10-degree, the reverse saturation current is going to double itself. And this fact is captured in this formula. So you have Is at temperature Tb. This will be given by 2 raised to the power of Tb minus Ta divided by 10 multiplied by Is at temperature Ta. And all the temperatures over here, Ta and Tb, are in Kelvin. So in the question, you need to see if the temperature is changing or not. If the temperature is changing, that means you have to first find out the corresponding reverse saturation current from there, and then the new reverse saturation current is going to give you actually the correct value of forward current. How do you get this formula? So this is again determined experimentally. I don't think any proof exists for this. So you carry out a lot of experiment, plot the curves, and then do curve fitting to see which equation fits in the curve, and that's how this formula has been obtained. So one thing now we know that reverse saturation current is going to change with temperature, which is governed by this formula. But since we know that the forward current is actually a function of reverse current, e raised to the power of v by eta vt minus 1. So if this changes, this should also change. Right? If this changes, this should also change. So let us see over here in this plot on the x-axis, say at voltage V2. So at voltage V2, I have the current I1. And this solid curve is at temperature Ta. Then again, we have a dotted curve over here, which is at temperature Tb, such that the value of Tb is greater than Ta. Now here at value of voltage equal to V2, the current at the lower temperature was I1, whereas the current at high temperature Tb is I2, and we clearly see that I2 is greater than I1. Now what happens with change in temperature? It's generally not good to have increase in the current, because diodes, when they are fit into the circuit, it's actually assumed that some fixed current is going to flow through it. So we do not want that with increase in temperature, the current across the diode should increase, because that increased current could damage other devices which are connected to that circuit. So in that case, what we need to do, we need to compensate for increase in temperature. That means even after I increase the temperature, I don't want my current to be increased. तो वो कैसे कर सकते हैं? Just look over here in this plot. So we see that at voltage V2, the current was I1 at temperature Ta. But if I increase the temperature to Tb, the current increased to some value which I do not want. So what I do is, in order to maintain the temperature constant, I see where this is intersecting with the shaded line. This intersects with the shaded line at this point, to which we have the corresponding voltage V1. That means because of increase in temperature, if I don't want my current to increase, then I should actually reduce my value of voltage. So decrease in voltage is compensating for increase in temperature, such that the current flowing through the diode remains constant. And by how much should I decrease so that I can keep the current constant? So again, these things are determined experimentally, and it has been shown that for every 1 degree increase in temperature, if I reduce the voltage by 2.5 millivolts, then in that case, I can maintain constant current across the diode. And this is true both for germanium as well as silicon diode. So this gradient of voltage with respect to temperature is given by minus 2.5 millivolts per degree Celsius. That means for every 1 degree increase in temperature, the reduction in voltage that I should do in order to maintain constant current is 2.5 volts. ठीक है? Is it fine?
Yes, ma'am.
Okay. So now if this is fine, let us start with the diode circuits. So I'll briefly introduce this concept and then we will close in a while. So here in this figure, a simple diode circuit is shown. So there is a diode connected across a resistance and then there's a voltage source. And we are required to find out the value of V, that is voltage drop across this diode, and what is the current flowing through the diode. So as it is, जैसे हम पहले करते थे, we will try and write the equation for these circuits. So first equation comes from the equation of current of the diode. So my first equation is I is equal to Is multiplied by e raised to the power of small v divided by eta Vt minus 1. This is my first equation. And then the second equation is, if I apply KVL into this circuit, then I will have V1 is equal to small v plus R into I. This is by applying KVL in this. So by usual techniques, what we could do, there are two equations and there are two variables. So what we can do is we can write the expression for I from equation 2 and then substitute this back into equation 1 and then solve for whatever variable is remaining. This is what we usually do. But this technique that we usually do is not applicable over here, because if you substitute the expression for I into this equation, the equation that will finally form will be a transcendental equation that will not have any analytical solution. That will not have any analytical solution. That means it will not be possible to solve that equation using the techniques that we already know. So in that case, what should we do? The other methods are, first method is the graphical method and the other method is by using numerical methods. So let us see what happens in the graphical method. So graphical method में हम क्या करेंगे? We are going to draw a graph for this equation. We are going to draw a graph for this equation and see where both of them intersect. So one example is shown over here in this figure. So first of all, I draw the plot for this curve. We know that this is simply the curve in the forward bias region. So until you have the cut-in voltage, the value of current will be 0. And then it's going to increase to some value given by this equation. So इसमें क्या करते हैं? Small v की अलग-अलग values रख के we calculate the corresponding value of I and have this curve. Then the next thing is to plot this second equation. So this second equation is actually the equation of a straight line, because if you rearrange this, you are going to get this equation wherein I is equal to minus 1 by R into V plus V1 by R. This is the equation of a straight line where minus 1 by R is the slope and this V1 by R is the intercept on the vertical axis. So this line is intercepting the vertical axis at V1 by R and this slope over here is minus 1 by R. And their point of intersection is this point. So it is assumed that this point is actually the point which satisfies this equation also and which satisfies this equation also. Therefore, the voltage and current at this point is the solution of these two equations. This point is also known as the quiescent point or Q point. So this is one of the methods. Other method is the numerical method. So numerical method, you must have read about numerical methods in your mathematics 3 course. If you have not yet studied mathematics 3, then I'll give you a simple idea. Numerical methods में क्या होता है कि I start with any arbitrary value of V. वो arbitrary value of V को I substitute in this equation for current I and then see what is the value of I. So what happens is, for a given value of V, I obtain some value of I as I1. फिर ये I1 को मैं क्या करती हूँ? दोबारा से V के equation में लिखती हूँ and then I get a more accurate value of V which is called V1. Then this V1 is substituted back into the equation of I, so you get more accurate value of current as I2. So this process is continued after many iterations. So what it is observed is 15, 20, 25 iterations हो जाएंगे, then you will observe that the change in current, like I say 30th iteration, I at 31st iteration and I at 32 iteration, this does not differ much. So when you see that the value of current in the successive iterations are not increasing by very large value, then you can say that, okay, one of these values is my required current, and by substituting that I in the value of voltage, you get the value of V. So this is another possibility to calculate V and I in these type of circuits. But as you can see from the explanation, it is not feasible always to do graphical methods as well as numerical methods. तो इसके लिए क्या करते हैं, we need to do some simplifications in the description of the diode. What we do is we define an ideal diode in that case. An ideal diode क्या होगा, ideal diode की characteristic ऐसे होगी. So what does this mean? This means that when the diode is forward biased, I will assume that there is no voltage drop across the diode and some finite current flows through it. What does that mean? That means if this was my diode, which is forward biased, then that forward biasing, I will just replace this by short circuit, because no voltage drop means short circuit of the diode. So earlier this current was I and there was some voltage drop V. This will be approximated as V equal to 0 and still some finite current I flowing through this depending upon what is the value of other circuit elements. This is the case of forward bias. And in the reverse bias, what we do? Reverse bias mein, we say that, okay, there could be some finite voltage drop across the diode, but in that case, there is no current flowing across it. So if the diode is reverse bias, that means I will approximate it by an open circuit. So this will be shown as an open circuit. So here you could have a voltage drop because there is always a voltage drop across the open circuit, but the value of current flowing through it is 0. तो क्या सिंप्लीफिकेशन हमने किया, रियल डायोड में हमने बोला था कि जब रियल डायोड रिवर्स बायस होती है, दैट टाइम यू हैव अ स्मॉल रिवर्स सैचुरेशन करंट फ्लोइंग थ्रू इट. सो व्हेन आई सिंप्लीफाई टू आइडियल डायोड, I will say that I am ignoring this small reverse saturation current and I will just say that no current is going to flow through the diode. So whenever you find a diode which is connected in a reverse bias fashion, you just have to replace the diode by an open circuit. Similarly, for a real diode, what was happening in the forward bias condition? So I said in the forward bias condition, if the voltage drop is over the cut-in voltage, then forward current will flow through it, and of course there will be some small voltage drop across the diode. So when you are simplifying the assumptions, in case of ideal diode, we say that I am going to ignore this small voltage drop and I will say that there is no voltage drop. So if you see a diode which is connected in a forward bias fashion, you can simply replace that diode by a short circuit, and if it's a reverse bias, then you can replace the diode by an open circuit. So this will simplify the analysis of voltage and current in the circuit to a very large extent, and at the same time the answer which is obtained is almost accurate. अगर एक्चुअल लेते तो जो आंसर आता वही आंसर ऑलमोस्ट आएगा आइडियल केस में भी. So we are compromising very less on the accuracy, but we are simplifying the analysis to a very large level. So here I will stop. In the next class, we will see applications of these ideal diode as rectifiers and as clippers and clampers, where we are going to use this concept that when the diode is forward biased, it is short circuit, and when the diode is reverse biased, it will be replaced by an open circuit. So if there are any doubts, you can ask now, otherwise we close.
Ma'am, in this numerical method, if one value of V gives one value of I, then that if we put I1, then how can we get new value of V? Won't it give the same value of V only?
So there are some approximations actually. I just gave you a very broad idea. So because we are actually not using this, so I will not go into the detail of this, but you can for now keep in mind कि उसको approximate करने के there are methods.
Okay.
ठीक है, ये मेथड्स इतने यूजफुल नहीं होते क्योंकि अगर न्यूमेरिकल मेथड लगाने बैठोगे फिर तो आंसर आ चुका. ठीक है. Any other doubt?
Ma'am, I had a doubt like in one of the questions of chapter 4,
Chapter 4, not from here.
not from your quiz में जो आ रहा है वो.
Okay, let me then close the recording and then we can discuss.